Okay, so I would like to have another like a mini lecture to talk about the diffusion reaction convection equation. This is so important to our class, so I think it was worthwhile to just discuss it a little bit, so give you a big picture. So now let's recall what is J flux. Flux J, it can be contributed by two mechanisms, which one is from Fick's first law is due to diffusion. So it's diffusion coefficient, which can be a function of space. So we use x. So now let's say x is x, y, z. It can be a function of space. Then you have gradient, like this way, the gradient of c means it can be like 3D gradient. Then you may potentially have a convection term, which is by the velocity itself can be a function of space multiplied by concentration. And then what I mean is our concentration is a function of space. Our diffusion coefficient can potentially be a function of space, and our velocity can also be a function of space. Now this is just a flux. Flux you have, we have a diffusive flux. Plus convection. All right. Now let's consider a control. I'm not going to derive everything from the scratch. I'm just saying if you have a control volume, so construct a control volume. Then based on what we call the conservation of mass. Mass conservation. You will find is the divergence of the flux. It gives you a reaction term. The reaction term itself can also be a function of x. So this is totally coming from the conservation of mass. Basically, it says the divergence of flux, if it's divergence free, means the delta dot of J is 0, then there is no creation or generation of material within the control volume. If the divergence is not 0, that means if it's not a divergence free, then there will be something going on in your control volume. Either something is being generated or something is being consumed, whatever. Now, if you plug in this, you will see you get an equation, which is, well, this probably is at a steady state. Maybe let me see, this is at a steady state. The non-steady state, you can show that the change of concentration over time equal to minus the divergence of J plus the source term. And in either case, you can expand it. So let's plug in the expression of J. As you can see, if the diffusion coefficient and the velocity, they are not constant, you cannot move them out of the derivative sign or the gradient, the divergence sign. But since you can, it's additive. Sorry, we have a minus. Since it's additive, you can sort of separate the two terms. So the diffusion term give you this guy. It's better to put an error on all the triangle just to show that this is the inverted triangular itself can be like a vector operator depending on how you use it. If it's a gradient, then it's a vector operator. If it's a divergence, you actually have a vector dot with another vector, then dot product give you a scalar. So this would be like a more straightforward or more clear way to show which one is a vector, which one isn't a vector. So sometimes people put the error on the gradient symbol just to be clear. Okay, then we have minus the divergence of velocity in a C. The reaction is always a scalar. Now this is 3D. 3D means you can have x, y, z, or maybe in general, you can also have x. You can also have x represent theta z in cylindrical coordinates, or x can be theta phi in spherical coordinates, or x, y, z in Cartesian coordinates, whatever. The x bar, the vector form, just means it's the 3D coordinate system, depending on which coordinate system you are using. So in 1D, Cartesian coordinate, they x and in this case, the above 3D form reduced to 1D. We still have partial because it's a function of both time and space. Now, in 1D, let's say the velocity is only along the x direction. So we just use a single v to represent it's a scalar vector. Now, if, let's say, if d and v are constant, we have the simplified form that we have been seeing. And under steady state, then it's not a function of time. We just have function of space. Then we can replace partial derivative to just a regular derivative. That's what we have. We have seen it a lot. Now, if B and V are function of space, then what we need to do is to take chain rule. So now for the derivative, first you have partial D, partial X, then partial C, partial X, plus B, partial squared C, partial X squared. Then the velocity is partial V, partial XC, minus V, partial C, partial X, plus R. This is use chain rule. And these terms are same as in the constant D and V formula, but you have two additional terms. These two additional terms, which comes from the fact that the diffusion coefficient and velocity is a function of space. And in the class, we had one example where the diffusion coefficient is a function of space. And we practiced this scenario. And I hope you remember that. And this is an example of this whole big picture when those parameters are not a single value, but a function. Okay, now on the steady state. Then you don't have d theta. Then you would have d. And on your equation with these three terms, I hope you're already familiar with at this point. And the additional terms are due to the factor that those are function of time. So once you have those equations, and then you are just going to solve this and then solve. Let's solve for C based on the given conditions. So these are differential equations, and the way you can solve for equations, well, also based on the exact expression, sometimes you may be able to do separation variables. If not, then you may be needed to use a combination of particular solution plus homogeneous solution plus separation variables. So for example, you may have tools of finding a particular solution, particular solution plus homogeneous solution. Or you may have something we call it separation variables. Or maybe use a combination of these or whatever. So this is a supplementary mini lecture I would like to give. So this was in the lecture, let's see which lecture, lecture 52. I had a side notes on the general diffusion reaction advection equation. However, because it was embedded in another like a video, so I think it was worthwhile to make it a separate one. And here I'm not talking about any technical details of solving any equations. However, knowing the big picture of this equation and this comes from the conservation of mass from the particles. And there is where you have used your flux, because when you build a control volume, you will naturally have flux, like in, flux out from one surface to the other surfaces. And here is where you use fluxes. And once you have the flux expression, you have conservation loss, and then you can generate it. So this is the, okay, let me put down this equation. This is a very generic diffusion reaction advection non-steady state, and it's not something like a mysterious coming out of nowhere. It comes from conservation of mass over a control volume. Okay, hopefully you can digest this, and make sure when you look at the in-class discussion problems and everything we have been doing, compare the way we solve it with this big picture and try to identify the major principle or the core principle behind, and that helps you to reinforce your learning about the subject. All right, thank you.